How does evaporation occur? And why are we going to discuss that with reference to diffusion of water and nitrogen? That's a great question. Let's start by using an example. Let's say we have a pool, and the pool is filled with water, H2O. Above the pool is a stream of nitrogen gas flowing. And above the pool, there's also a screen so that there are no pressure changes that occur. Much like a bottle of water, if you leave the lid open, some of the water will evaporate out after a while, and that can be seen in a problem like this. Let's use Fick's law first to determine how the diffusion is going to occur. Fick's law is the diffusion from a high concentration to a low concentration. Writing out that equation, we get something along the lines of J is equivalent to diffusion coefficient, and J is equivalent to our molar flux, right? Molar flux. Our diffusion coefficient is going to explain to us how likely a material is to want to diffuse, or something is want to diffuse. And in reference to that, a diffusion works with a concentration gradient. So we're going to multiply that diffusion constant by a concentration gradient. So you have the distance it travels over the area, and then multiply that by our concentration, negative concentration, because you're going up from 0 to 1. And 1 is just a number I chose. You can also consider it L. Remember that in between our pool and the nitrogen gas is a combination of nitrogen and water. And you have to think about that concentration. Let's look at the units of each of the components of our Fick's law. We first have our concentration, and that's going to be moles over our volume, our liters, which is N over V. And if you understand a basic law, PV equals nRT, you can clearly see that N over V is equal to P over RT. Continuing on, we want to find that concentration, right, of the nitrogen and the water. And that's not going to be 50-50, or it might, but we don't know that for sure. So we'll have our nitrogen, our concentration of our nitrogen, plus our concentration of our water. It's going to be equal to the total concentration. So our pressure over our constant multiplied by the temperature plus our pressure for our constant multiplied by the temperature. Remember, these are each concentrations of that material. Here's a general equation. Now we've just set up a general equation to find the total concentration for our nitrogen and our water, which in turn finds the concentration for each of our nitrogen and our water. But in order to really get down to what that concentration is, we need to understand what's going on in the problem once again. Because there is a screen over top of the pool, there is no pressure change, like I said in the very beginning. So no pressure change. And there's a concentration gradient, as well as a steady state. Graphing that, we'll graph it over this distance dz. So dz, our concentration, will have 0 to L, and then concentration could be whatever numbers. It will just increase as it goes up the y-axis. Our water, as it goes further up the pool, will decrease in concentration, right? Because it gets closer to the nitrogen gas. And so logically, you'll have more nitrogen gas than water. So that will decrease. But our nitrogen gas at the very top of the pool, where the screen is going to be at its highest point. And as you go down from the screen to the water, it's going to decrease in concentration. So there, now we've graphed our nitrogen and our water. Unfortunately, this isn't true. Our nitrogen doesn't decrease in concentration that goes down to water. If you notice, as the nitrogen diffuses down towards the water, it has nowhere to go. Our water diffuses in the opposite direction, but our nitrogen will hit this barrier and just stay there. So what does that mean? Well, let's look back at Fick's law, and we can use the overall flux with reference to our molar flux in order to determine how this works. We have Fick's law, and Fick's law is our molar flux is equivalent to negative concentration multiplied by our diffusion coefficient multiplied by the concentration gradient. That's not a 2, that's a 1. And our overall flux is equal to our molar flux plus x1 multiplied by our flux. And this n, that's equivalent to N1 plus N2. And each of these is in reference to each of the chemicals being used. So this would be N2, like nitrogen gas, not this N2. It would be nitrogen gas, and the other one would be water. This N1 is equal to 0. The N for our nitrogen is equal to 0. Now, why is that? Well, our pool has the water diffusing upwards. Our water is diffusing upwards towards the screen with the nitrogen gas going in a direction, and our nitrogen gas is moving downwards, and it needs a positive flux to go somewhere. This is in the z direction, but it has no place to go. So it's using its energy to go nowhere, just stay in the same position. So our n is equal to 0. Let's write an equation to also show that. We have our flux of our nitrogen, and we want to show that there's a positive flux, but it eventually equals 0. That's equal to our molar flux plus y, our nitrogen as well. It's percentage of our nitrogen. X is equal to usually a liquid, while y is a gas. So our nitrogen is gas. That's why it's YN2 and not XN2. Which means that this X right here can be a Y. And for our flux, we know that this Y has to be multiplied by our entire concentration or entire flux, which is the water and the nitrogen. But our nitrogen flux is equivalent to 0. Both of these are equal to 0. So 0 is equal to our molar flux of our nitrogen plus Y of a nitrogen multiplied by our flux of our water. If we rearrange this equation, we get that our molar flux is equal to negative Y nitrogen of our flux of our water. And this is how we're going to find that diffusion of our water and our nitrogen. Let's put actual numbers to this problem in order to solve it. So let's say that our temperature is equal to 50 degrees Celsius. Our pressure is equal to 1 bar. And our diffusion coefficient is constant for the gas, and it's equal to 10 to negative 5th meters squared per second. Look at those numbers right there. We'll take them to the side so we can see them even better. Let's convert these numbers to something that will be a little more useful for this problem. So our temperature, we'll convert that into Kelvin. 273, that's going to be 323 Kelvin. And this 1 bar is equal to 1.013 times 10 to the 5th pascals. So from here, we want to find our mole percentage of our water. We use our flux is equivalent to our molar flux of our water plus that Y our water multiplied by our total. Remember, N is equal to NH2O plus NN2. We also know that Fick's law is our molar flux is equal to negative concentration multiplied by the diffusion coefficient multiplied by that concentration gradient. So plugging both of these concepts back into this equation we just created, we get that the flux of our water is equal to negative concentration, diffusion coefficient, concentration gradients, plus our percentage of our water times NH2O plus NN2, and NN2 is equal to 0. From here, our concentration is equal to P over RT. Remember that. So remember that, and that constant fixed law. Concentration is P over RT, pressure over our constant times our temperature. And we also want to use two different concepts, or you can use two different concepts depending on what information you have. Antoine's equation and Clausius Clapeyron. So Antoine equation is log 10 of our pressure is equal to A minus B over temperature plus C. And A, B, and C are given to you usually. And if you have those available, and then for our Clausius Clapeyron, assuming that the gas behaves like an ideal gas, we have the natural log of P1 over P naught is equivalent to our negative change in enthalpy of vaporization over our constant multiplied by 1 over the second T1 minus T naught. So these will be used to help find your pressure that you can use to find the concentration. For this specific problem, I just found that the pressure of the water at 323 degrees Kelvin is equal to 12 times 10 to the negative third pascals. So if we want to find the pressure of our nitrogen, you know that the P total is equal to the pressure of the water plus the pressure of the nitrogen. Our total pressure is 1.013 times 10 to 5 pascals. That's equal to 12 times 10 to the third pascals plus our pressure of our nitrogen. So ultimately, the pressure of our nitrogen is equal to 8 times 10 to the third pascals. Now I'm going to go back up to our equation and rewrite it, simplify it, to get that our flux of our water is equal to negative, remember this identity, pressure over our constant multiplied by our temperature multiplied by that diffusion coefficient. And that's going to be multiplied by our percentage of y over the area plus YH2O multiplied by flux of H2O plus 0, but I'm not going to write that 0. Once again, rewriting this, we get that our flux of our water is 1 minus YH2O, and that's equivalent to negative pressure times diffusion coefficient over constant multiplied by temperature times the partial derivative of our YH2O over dz. I would like this dz to come over to this side, and this 1 minus YH2O to go over this side so that the derivative can be taken. So this final equation that we will then take the integral of is our flux of our water. It's equivalent to negative pressure, diffusion coefficient, over constant times temperature, times derivative of YH2O over 1 minus YH2O. In order to find the limits that we're going to integrate our YH2O by, we need to do some calculations. For our z, our distance that we're moving, it's from 0 to 1. So that's already figured out, but for our y, it's not as simple as you would think. Let's go back over to the pressures that we just calculated right here and determined. Our YH2O, it's going to be equal to the pressure of our water over the total pressure. So we have 12 times 10 to the third pascals over 1.013 times 10 to the fifth. That's going to get us 1.2, or sorry, that's going to get us 0.12. For our z, that is just from 0 to 1, and our p is going to be from 0.12 to 0, right? It decreases, it doesn't increase. So let's integrate. Our our molar flux is a constant, and this whole part of the equation is a constant. It's not going to change with respect to the integral. So you want to take that outside of the integral. dz from 0 to 1 equals negative ed for rt. Take the integral of 1 over 1 minus yh2o from 0.12 to 0. That integrates to be flux of 1 equals same constant. Of course, we took it out, doesn't get integrated, times the natural log of 1 minus yh2o from 0.12 to 0. Also take the negative sign right here and place it inside of our natural log to get something that's a little easier for our brains to comprehend. Instead of 1 minus yh2o, it's yh2o minus 1 from 0.12 to 0. So that we plug in all of our numbers, our pressure. So we're going to do our pressure, which is 1 times 10 to the fifth pascals multiplied by our diffusion coefficient 10 to the negative fifth meters squared per second over our coefficient of 8.314 joules per mole Kelvin times 323 Kelvin, all times the natural log of 1 over 0.88. If you do the math, you get 4.76 times 10 to the negative 5. But what are the units? It's not very clear right now, right? You don't see what cancels out what. Take our pascals, which we know is newtons per meter squared. And newtons is equal to kilograms meters per second squared times our 1 over meters squared. That's going to get kilograms over second squared meters. Our joules, what are joules? Joules are newtons times meters. And again, our newtons are kilograms meters over second squared times meters. So kilograms meters squared over seconds. Let's see all the units that are within here and take them, put them all in one little division symbol. So our kilograms, this is on the bottom, and then for our meters squared, seconds are on the bottom, our joules are on the bottom, so that means that kilograms times meters squared on the bottom, but our seconds are on the top, and our moles are on the top, and Kelvin is on the top. Kelvin is also on the bottom. Cancel out certain units. These meters squared can go. These seconds squared can go. That's moles, kilograms, moles, meters, seconds. Kilograms again. So we just get moles per meters, seconds. So our final answer is moles per meters per second. So this number is our estimated molar flux within our pool of our water. We did that by determining how to find that molar flux with reference to the amount of each material or element or compound within the pool, and then used Fick's law as well as Antoine's equation or Cauchy's-Clapeyron equation and general knowledge like C equals P over RT because PV equals RT in order to find that our molar flux for our water is equal to 4.76 times 10 to the negative fifth moles per meters seconds.